movie of a volcano erupting over and over. Joe Dufek from some school, from Georgia Tech.
All right. So the goal of what I'll be talking about today is try to describe some processes that lead to eruptions like this through the perspective of multi-phase flow. And also I'll be talking about a lot of things in the crust and a little bit above the crust. And I'll only briefly mention the mantle, but it's obviously the important driver of all the stuff we see here. If we look at an explosive eruption like this picture of Mount St. Helens with a little cartoon superimposed, there are obviously lots of multi-phase flow aspects to this eruption, all the way from a volcanic conduit that has bubbles that are exsolving, that are driving the explosivity of the volcano, to the stuff we just saw a video of, which is actually mostly volcanic glass in a turbulent flow. And if it's buoyant and entrains out of atmosphere, it'll go form these Plinian columns. If it doesn't, and it's denser in the atmosphere, it forms a pyroclastic flow or pyroclastic density current. But the other aspect of multi-phase flow with regard to crustal systems are magma chambers. And I'll be talking probably mostly about magma chambers today in reference to how you produce eruptions like we saw in the previous slide, which is a rhyolite. So how do you produce this really high silica scum of the magmatic world? How do you produce this? And so I'll talk about some ways multi-phase flow gives us insight to that. And then throughout that, this talk, I'll try to piece together observations of timescales and link dynamics to those interesting observations of timescales. So just to orient us, I'll be mostly talking about subduction zone systems. So this is a cartoon from a recent review paper by Jagwitz and Kelman. And so the idea is that we have the subducting plate. It's releasing volatiles, inducing melting in the wedge. I won't talk about this process, but it is another really interesting multi-phase problem, as we've kind of alluded to. Then that melt, primarily basalt with lots of dissolved water, enters into the crustal system, and that's where I'm going to pick this up for most of the talk. I'll get into a little bit of numbers here in a second. Yeah. Oh, the numbers on here. There are timescale estimates that I'll talk about. That I'll allude to in a bit. So one of the nice things about these sort of crustal systems, there are lots of different data available to us. We have things that are erupting that give us eruptive products. From some of these eruptive products, we can get at timescales from diffusion or radiogenic isotopes. And there are also geophysical measurements that give us an idea of what the active systems are looking like at that particular moment. So things like tomography or deformation data. But these two kind of views are very different in some sense. This is some sort of integrated view. It's measuring something that happened in the past, whereas the geophysical view is ongoing. And so I'm going to try to piece together a lot of these timescales with some dynamic overlay. And this is my really simple cartoon of the different pieces of the system. These little bars are meant to qualitatively indicate the amount of time we spend with the magma in different parts of the system. And certainly we can go from, say, the upper mantle all the way to the surface in very fast timescales, as we'll discuss in a moment. Or we can take longer time and eventually erupt. So the idea of this cartoon is, and I'll try to be more specific in the next few slides, is that we have relatively short timescales going from what we think is release of fluids from the slab all the way to the surface in some cases. We probably spend a longer time in some instances in lower crustal magmatic systems. And then there are some really interesting processes going on in the upper crust in terms of some of these reservoirs in terms of residence time and extraction timescales. We think extraction timescales can be relatively short. And then I'll talk a little bit at the end here about the eruption duration of very large volcanoes, so volcanoes that are erupting 100 cubic kilometers of magma. So these are very short timescales. And the questions I want to kind of keep going back to, I'm not going to answer all these questions, but I think they're worthwhile keeping in mind as we're going through the dynamics discussion is really how are we producing continental crust? And at its essence, that's what we're really going to be trying to get at. And how do we build these big silicic reservoirs that I'll talk about, and ultimately what are the dynamics of some of these eruptions. Okay, so just to review a little bit of what we know about timescales, this is a review paper actually from Simon Turner and co-authors from quite a while ago now. One thing they're observing and this is for island arcs in particular, is that there is radium-thorium disequilibria that we can measure at the surface. And the typical interpretation, and I think this is pretty robust and for most of these magmas, is that this disequilibria is being generated through the release of fluids at the slab. So this is interpreted as a measurement of time from basically the slab to when it is erupted and measured. So these are very large disequilibria, if you remember back to our discussion of disequilibria from Monday. So you have probably very fast time scales. So I have the kind of usual number, which is sort of the analytical capability, but this sort of large degree of disequilibria is probably less than one half-life. So it's very fast. And this is just a cartoon that Simon put together indicating this. Indicating relatively fast extraction to mantle, and then it could stall at different points along the pathway here. There's a lot of discussion about lower crustal magmatic systems, and I'll pick up that discussion later, as well as upper crustal systems. And certainly in island arcs, this whole throughput is relatively fast, anywhere you can measure this disequilibria. So just to, if you haven't forgotten, it's about 1,600 years is the half-life of radium. So you have that piece of the puzzle, but then you also have measurements from typically continental arc magmatic systems. These are from accessory phases, primarily zircons, uranium, lead, and uranium thorium measurements, indicating that at least for some systems, you can have very long duration magmatic incubators. And so you can kind of get a sense here. These are timescales that are going up to hundreds of thousands of years, if not longer. So you have this contrast of really fast time, probably going through the mantle wedge, but then occasionally you sit and stall in the crust for very long periods of time. So how do you put those two contrasting timescales together? The other piece of the puzzle that is a bit of a conundrum is that, yeah.
I missed something. What's the x-axis?
This should just, it has nothing, yeah. It's basically different systems, yeah.
Is that a half Caltech?
It's a half Caltech plot, yeah, if you want, yeah.
Everyone's a Caltech postdoc. She picked it up from us. I see. Okay.
Yeah, maybe that's it. Yeah. The other odd thing, or the other thing to keep in mind, is that the magmas coming up from arcs are predominantly basalts, but the continental crust that we have, we think at least, is a little bit more silicic than the melts coming from the mantle. And this is a bit of a mass balance problem, but the problem I want to address today is really how do we get to these higher silica contents? So how do we go from a basalt to these higher silica contents? And the third piece that I want to kind of look at in a little bit more detail is how do you produce what has become kind of a very interesting observation in lots of systems like this, where you get composition gaps. So these are sometimes called Daly gaps from Daly's observations. But the idea of this is that you have a gap in composition, so this could be plotted in silica between one composition and the other. So why is this not a nice continuous histogram? Why are these little holes? And I'll try to describe or discuss some ways to do that. And these are lots of observations like this, and it's certainly been pointed out since Daly. So this is another plot. I guess this would be another Caltech plot in a way. Of different systems. There's nothing special with this ordering here. It's just been ordered so that there's higher silica gaps at the bottom than at the top. And you can also, these are all in silica, but you can also plot these in other oxides as well. And what we'll see is that the phase equilibria, what crystalline phases you're producing, will play a big role in where these gaps might be. Okay, so I'm going to kind of use these gaps as a way to start to introduce how multiphase physics and thermodynamics can be used together to try to start answering questions relating to metrology and geochemistry. And anyway, we look at it, the way we're going to produce the silicic upper crust, you can kind of have two major dials that you can play with. You can either do it through crustal melting, so partial melting of the crust, or you can do it through some sort of fractionation process. You have an intruding magma, you remove some of the phases, and you're left with a higher silica melt. So you have these two dials that you can play with, and I'll play with these two dials a little bit throughout. I would say that melting has often been favored as kind of the preferred way of doing this, but as we'll talk about a little bit later, I think it's obviously a mixture of the processes, but one of the reasons it has been argued as a really good way of producing these high silica magmas is it's been argued as an efficient process, a thermally efficient process. And we'll see that, that in the end, it turns out to be a little bit more complicated than that. Okay, so the idea now is to try to see if we can't link in some of these time scales with this observation. And one of the things that our group and lots of other groups have looked at is how much melt you can produce. If you have basalts coming from this arc system intruding into the crust, how much can you melt the crust? And what controls that melting? This is one example, and I think it actually goes along very well with Paul's talk from the first day. This is an example, and we'll see another type of example later on, where we used a parameterized system to look at melting reactions. So we're not solving for the full thermodynamic problem. We're using just some relationship between temperature and melting that's based upon experiments. This particular melting relationship is for an amphibolite. So the idea here is that we're dehydrating or heating an amphibole plus plagioclase mixture and producing a melt and pyroxene and garnet if it's deep enough mixture. If you look at this, this is just a stochastic intrusion of basalt into the crust. If you look at this problem, you can play around with flux, and you can play around with the initial geotherm, time of intrusion, and so on. And this is kind of a summary plot for one set of conditions showing time on this axis and depth of the crust. And what I'm plotting here is volume of crustal melts versus volume of mantle melts. So how much melt do I have sitting around of each reservoir through time? And you see as we get hotter conditions, we're tending to get a little bit more of the crustal melt in our fraction, and this shallower crust situation, we're getting more of the fractionates dominating the system. Okay, so if it's relatively cold, we're going to tend to bias ourselves towards fractionate products. If it's very hot, we're going to tend to bias ourselves towards actual crustal melting. Now you might argue, okay, well this is a stochastic process, and we, real intrusions probably aren't stochastic. They're influenced by tectonics. They're influenced by stress. And so others have done calculations. This is a nice calculation from Leif Karlstrom where he looked at having a overpressurized magma chamber that creates a stress lens so that dikes intruding into the crust are going to be focused into it, so you get more flux of magma into the system. Claude Jopard has kind of a very complementary sort of approach where he had a volcanic load at the top, which has a very similar effect. You can focus in more melt. You can imagine tectonics influencing this as well. But one thing we found with looking at all these calculations and then going back and looking at a lot of other thermal calculations that lots of people have done is that even if you have all these sorts of different effects, what you find is that typically it's very hard to produce lots and lots of crustal melt when you consider the amount of enthalpy it takes to do this. So it's a relatively inefficient process, and so the rule of thumb I put up here was 10% efficient, and what I mean by this is if I took all the enthalpy that I would use in a back-of-the-envelope calculation. So if I say they have an enthalpy from a mafic magma, and let's say I can only zap a part of the crust using that enthalpy, that would be 100% efficient. But it's not too profound, but when we're intruding magma into the crust, we're diffusing lots of heat, and a lot of that heat never goes into actually melting the crust. You lose an inefficient process, so you lose 90% of the heat in that process. So it's actually really hard to get lots and lots of crustal melt in this system, and partly because of that, then we thought we had to explore either different ways of crustal melting or different ways of looking at fractionation, and that's really when we get into the multiphase problem. That was the motivation. And we also felt like we needed to move away from parameterized approaches to the thermodynamics. So what I'm going to describe for the next 20 minutes or so is a combined model where we have a multiphase flow approach, but then we also use a thermodynamic model. I say melts here. It's actually a version of rhyolite melts. It's going to be our thermodynamic solver. And we're going to use this solver to decide how enthalpy is partitioned between sensible or latent heat. And we're also going to use it as a way to keep track of what different phases are being produced, what oxides are around. And so it's nice in that you can get chemical information from this dynamics model and in that way compare to observations. I've noted a few other things. So one of the things, since we're using a thermodynamic model at equilibrium, we have to assume that we're close to equilibrium. in some ways, the equations lend themselves more towards thinking about these things as kinetic processes. So if we had a better way to get at that, then that would be advantageous. But for now, we're just going to assume it's very close to equilibrium. And as Chris alluded to, there's a lot of work that still needs to be done in thinking about drag between phases. And I think I want you to kind of keep that in mind as we're going through this process, is that we have a broadly parameterized formulation for drag between melt and crystals. It's a little bit like Chris was talking about in terms of viscosity. We're couching everything mostly in terms of drag. So just keep that in mind, that we have to make simplifications because we're going to solve this at a continuum scale. Okay, the main thing I also want to point out is that I'm going to use a particular metric so that I can apply this sort of approach and make a link between these sort of observations that we see in nature with the fluid dynamics calculations. And so I'm going to call this, this metric, a probability of extraction. And what I mean by this is I'm going to keep track of the relative velocity between the melt and the solid. And I'm just going to integrate over all time and space and normalize that. And it'll give me a distribution. And I really want to see, where is the melt really efficiently separating from the solid? Is it uniform through all crystallinity? Is it linked in particular parts of the crystallization space? That's kind of what this metric is going to give us. And the idea, it's not a perfect metric, but the idea is to try to give us something that's as close to what you would get if you went out to a big volcanic sequence, measured it at very high resolution, and then made a histogram of that. This would be close to what you would get. Okay, so these are the equations that we're looking at. One thing you'll notice from equations we've been looking at prior to this is that we are retaining some of the inertial terms. That's because the Reynolds number in some of these flows that we'll look at, particularly some of the eruption cases I'll look at the very end, are non-negligible. So we're retaining inertia. I'll show a scaled version of these in a moment. Just a few things to point out is that we're solving for several sets of crystal phases. So we have, in theory at least, several crystalline phases, so say plagioclase, pyroxene, et cetera. And so we have different conservation equations for these different phases. And then the big piece here is adding in the thermodynamic driver. So in all of these R terms, these are terms where we're, say, crystallizing or producing melt. So we're having phase change, so they're complementary terms in conservation of mass, a little bit of momentum, and thermal energy, and then, of course, conservation of chemical species. This is a kind of a big bookkeeping issue because we have to keep track of all the oxides. So those of you who have used melts or rhyolite melts, you know you need to put in all the oxides. And so for us, this is just keeping track of where the oxides are in space and time. Okay, and then again, the way these phases communicate with each other are through these reaction rates, or approximations to reaction rates, and then also through drag, so that one phase exerts drag on the other phase. Yep.
Go back just one.
Yeah.
Your in the conservation of momentum, your crystallization curve, that's RK. This is what's UKI is a derivative on?
Oh no. I should explain these indices. So this is just written. So I indicates the different spatial directions. I should equal 1, 2, and 3. K should indicate the different phases. So you have K equations for the phases.
Does that have is that Galilean invariant?
This momentum exchange term, or
yeah, because it's just a function of velocity rather than a relative velocity.
Yeah. I guess you should be U minus the other. It should be a separation velocity. Yeah, that's right. Because you're basically dumping momentum from one phase to the other. Yeah, that's right.
And your reaction term, how do you define it?
So this is as close to equilibrium as I can. So I know a time step from my dynamic simulation. I calculate melts, basically how much I melt from melts, and then make sure that it enforce over those kind of time scales. So it's as close to equilibrium as I can get. Yeah. So it's written as a reaction rate, but it's really trying to keep up with equilibrium as fast as I can. And this is, so it's naturally kind of written almost as to think, it'd be more natural to write this in sort of a kinetic expression, but we're not there yet, I'd say.
Are you using the actual differential enthalpies from the melts calculations, or did you make up some latent heat constants?
No, we used actually used the partitioning from melts. Yeah.
That's what goes into R, okay, or that's what's going.
That's what goes into L here. And actually, we'll see here, this is actually a major difference. This is, I think Paul put it perfectly when he said that one of the nice things about thermodynamic models is first principle models is they can surprise you. They have the capacity to surprise you. And this is one of those terms that surprised me.
The Nussel, is that Nussel number or TM minus TC? What is that?
Yeah, so this is just a parameterization for heat transfer between phases. Yeah, so we're dumping heat between phases.
K is the phase.
K is connectivity, I guess.
Subscript.
K is a generic phase, but you have TM minus TC. So
Yeah.
M is here.
Yeah. These are referring to melt and crystal, I think. Yeah.
Oh.
Yeah. Sorry.
But another half hour on this.
Yeah,
one.
yeah.
I know.
You're in the right place for it.
Yeah, that's right. So I just want to show, because I'll be showing some of the higher Reynolds number stuff later, I just want to show one potential scaling of these equations, particularly from the momentum equation. And for the case of eruption dynamics, we can get terms that look like Mach numbers, things that look like Reynolds numbers. And the last two terms are a Stokes number and a Froude number. And so, again, this Stokes number is talking about this exchange or drag between different phases. And so Stokes number, if you haven't encountered this before, is a ratio of the time scale of response of a particle to the fluid time scale. So a really small Stokes number would be a tracer of fluid flow, whereas large Stokes number particles have significant inertia. And I think this is maybe seen a little bit easier if you look at a Lagrangian equation. I won't show many Lagrangian results today, but if you look at Lagrangian equations scaled in a similar way, here I'm using V to indicate the particle velocity and U to indicate a fluid velocity. You get, again, a Stokes number and then a Froude number as well. Basically, this is for the gravitational settling here. And several people have done some really great studies looking at the impact of Stokes number on fluid flow. This is a paper from Tang where there's a blunt body upstream here, and it's indicating these vortex shedding events. And they've seeded this with particles with different Stokes numbers. So as you get the higher Stokes number, cares progressively less about the fluid flow in terms of tracing it out. And something similar here, this is Eckert Mayberg and his student did this, where they have these vortices that are stationary here, and then they're looking at settling of particles through these. And you get a lot more sorting associated with smaller Stokes numbers. This will become important as we start to think about how particles can separate from the fluid. Okay, so we have these conservation equations. I think one of the advantages we kind of mentioned is that we can use melts to calculate latent heats because they're not constant. And everything we'd been doing before this was assuming sort of constant latent heat. But they're not. It's nice because it provides some geochemical information and allows us to basically look at a wider parameter space than we were able to in the past. Before we would kind of fit a curve for a set of experiments, but now we can look at a little bit more. The downside of this, I put this kind of as a positive. Oh, it's parallel, but the downside is it's parallel because it has to be. It's a huge problem that we have to deal with, right? It's a big calculation, and I wish we could make it more efficient than it is, but so far it's not too efficient. Okay, so in terms of thinking about this latent heat curve, I just wanted to show one example. This is from a magma from Cotopaxi. It's a volcano in Ecuador that I'll talk about in more detail in a second. And if I showed you earlier melt fraction to temperature relationship. So for this black curve, just pay attention to this temperature axes and melt fraction axes. And you see that this is not linear, but it's not an exotic function either. But if you look at a corresponding sensible to total heat or latent heat plus sensible heat curve, so look at this axis versus melt fraction, you see that this is far from constant. And what you're seeing is different phases coming in, and so you have this sort of jagged curve, and latent heat's varying quite a bit throughout this system. You might say, well, that's kind of interesting. This sort of thing makes quite a bit of difference, actually, when you're doing the thermal calculation, though. So the way, I've simplified it compared to what most people do, but this is kind of the viewpoint we might have from the past, where we have some melt fraction to temperature relationship. This is linear to make it really simple and easy. We might use that to create an effective heat capacity in the most simple case we can envision, where you have a constant latent heat over a delta T, and that might be what we use to model the thermal evolution, but as we just showed here, latent heat is highly variable, and so this sort of effect has a big implication for how long you can keep melt in the crust and how much melting you can do. And we've certainly worried a lot about in the last 5-10 years about the temperature dependence of, say, thermal conductivity. It turns out this effect is actually bigger and more important than that sort of effect. So this is something that we need to really worry about, but we just hadn't. And we hadn't because we just assumed the latent heat was constant over different crystallization ranges. Okay, so if we then apply this is one generic calculation to show one example. If we apply this, the sort of geometry or the sort of fluid flow field that we get here is really simple. So all these calculations I'll show are like a really, really simple toy problem. We have a sill-like intrusion. It's a box, different aspect ratio, and we start off at the liquidus of the magma that we're looking at, and we let it crystallize. And as it's crystallizing, it's setting up dynamics. A lot of the dynamics are actually driven by the crystals themselves. There's quite a large density contrast with most of the crystals and the melt, and that drives some of the dynamics. The Stokes number in almost all these cases is very small, so the particles in the fluid travel together fairly well, or fairly closely, and it turns out they have the largest deviation from traveling together as we start to get more and more particles concentrated at the base of the system in this case. Okay, so what I'll show you, in a second is these probability distribution curves for extraction. But what I want to kind of indicate here is what these curves themselves are kind of being influenced by two major effects. One is a thermal effect, which just is going to set how much time you'll spend at any particular crystallinity. So if you intrude something on its liquidus, it's going to have really strong thermal gradients. It's going to drive it away from that very quickly. And the other effect is a mechanical one, and that is how quickly do we physically separate out the crystal from the melt. And so when we have these small Stokes number particles, they do separate from the melt a little bit, especially in this kind of detrainment area. But it turns out it's not super simple to just kind of rain out these crystals from the melt, especially for the higher silica content melt. These are pretty viscous systems. And it turns out if we're kind of looking at the optimum place to extract, it's somewhere, depending on our models for drag, between hindered settling and sort of this high permeability flow. It's going to be our optimal place to get the highest relative velocity. Okay, so we have the two systems. Yeah.
Do you have something in the equations that allow for the crystals to grow and coarsen? I mean, to undergo some sort of Ostwald ripening?
No, there's nothing like that.
Lava Salamata did? Okay.
No, nothing like that.
Not even, I mean, it would sort of affect the drag terms, especially.
Yeah. No, absolutely. Yeah. But there's nothing like that in these calculations. No. Yeah.
It's not obvious why relative velocity of the liquid and the solid is the right thing to ask about eruptibility. I mean, if I were to sample that liquid, I don't need to get the solids out of it. I'll just grab the whole thing at low melt fraction.
Yeah, that's right. And I don't think this really has to do with eruptibility. So, whether there's certainly been arguments people have made about, what's eruptible versus crystallinity, but this is not really getting at that question, I don't think. I think this is getting at, if I were to randomly sample this system, what's the likelihood of finding a certain crystallinity? And I'm assuming nothing about actual eruptibility. So it's really, I should be extraction efficiency, not eruptibility.
Is it about time spent in these different stages then?
Yeah. So when we combine these two, hopefully I'll show that. Yeah. So when we're dealing with probabilities, that has a big effect, and that's really the thermal problem. Yeah. Okay. So in cartoon form, if we just look at the thermal problem and we assume really a simple case, we might assume that we spend relatively little time at low crystallinity and relatively high time at high crystallinity. In terms of the separation case, that's going to make it a little bit easier. We're going to have a little bit more, change this curve a little bit at the low crystallinity case. And as we start to cut off our permeability, then we'll really affect extraction at the far end. Right? And so this still obviously is implying something about how drag is between these two phases. So this is going to move around a little bit depending on what you assume for that.
I'll be seeing that liquid composition.
There's a superposition.
Yeah. Yeah. Okay, this is just showing one set of example calculations. And so the way I would interpret this probability of extraction, this is our initial magma, that little red bar. This is all written in terms of crystallinity. We get this curve for different viscosities of magmas, if you will, that are kind of overlapping each other. Notice that there's no time on this curve, so I've collapsed everything because I'm just looking at integrating over all time. We get this kind of optimal extraction window in part because of the thermal, actually it's largely controlled by the thermal problem, but also modified a little bit because of this drag issue as well. So you can move this around a little bit by different assumptions about drag, but it's not extremely sensitive to this. But we certainly could do better, I think. Okay, this tells you a little bit about some sort of generic calculation. What I want to do now is apply it to some specific systems to see how I think this could be used. And one place that we can look at this is at coat epoxy. It's a volcano in Ecuador. It's known for sort of bimodal volcanism in that it has largely andesites or basaltic andesites and rhyolitic eruptions. And that's indicated in these chemical plots here. Most of the little eruptions we see, even recently are basaltic andesite. There's some larger rhyolitic eruptions in the past in this area. And so if you do calculations like I showed for this coat epoxy system, you use the composition of the andesite and you look at different depths of these calculations, you'll see that the phase equilibria, even though the crystallinity window is very similar at different depths, the phase equilibria will change the width of that gap just by what phases are stable. And we see that you get progressively less gap. This is not very realistic, these really high depths. But you get progressively less leverage as you go to greater pressures. And so the highest silica rhyolite you can get will be at the kind of the shallowest part of the system. And so if you apply this, one way to use this then is to think that this may be extracting these rhyolites at pretty low pressure then, right? And this is corroborated a little bit by the phase equilibria that we see in these systems. The other things that we can play around with, because we're keeping track of all these phases, that I think is kind of interesting. One of which is you can obviously compare modal abundances, which work fairly well in these sort of systems. You can keep track of what phases should be there. But you can also start to play games with thinking about radiogenic isotopes, and also start thinking about when we start to crystallize zircons and so on. And so that's what's shown here. And what this sort of boomerang pattern here is a simplification that the idea is that we have zircon in our melt. We're going to be removing, or we're going to be increasing zircon as an incompatible element as we crystallize. We'll start to then eventually get saturated in zircon and produce zirconium. That crystallization of zirconium will then drive the zircon down in the melt. So you get this kind of upside down.
Every time you said zircon, say zirconium, and every time you said zirconium, say zircon.
Did I say it wrong? I'm sorry. Yeah. So we should increase zircon. We should increase zircon on the melt.
Zirconium.
No. Here we shouldn't. There's no zirconium yet. So here there's no zirconium. It's just
Zircon
zircon.
is the mineral. Zirconium is the element.
Yeah.
Zirconium and ppm.
Yeah. You're right. Yeah. Okay, sorry about that. Yeah. That's right. So we start to produce zircon at this point in the shaded region, and then we'll drive down zirconium. Sorry about that. Okay, so this is a modeled section of this where the zirconium zircon saturation line should be here. We've hit this when we've reached about 0.4 melt fraction, and we make some simplifications about how much zircon we make, and you can get this sort of downward pattern to fit this data from Jenny Garrison. Okay, so this produces a gap that we see there, and we can also kind of fit this downward trend from the crystallization of zircon. That's kind of interesting, though, because that tells us when we're zircon saturated in the system, though, and from that we can start to think about timescales, right? And so what I'm showing here is kind of a messy plot, but is different aspect ratios with little timelines next to it. So these different systems are progressively larger volumes. The red here will indicate, I'll move forward, the red will indicate these optimal extraction efficiency timescales. It's actually starting to put timescale on this extraction. The green here just indicates where we've crystallized 25% of all the zircon we crystallize. right? So there'll still be zircon crystallizing. I just picked this as a random or arbitrary metric. We can then compare this to some things we know about the rates of andesitic magmatism at coat epoxy and the rates of rhyolitic magmatism. We see that, in terms of the rhyolites, we have recurrence rates of hundreds or thousands of years or so. So the simplest interpretation of this is that you erupt your rhyolite, you sit around for a while, you produce more rhyolite, and you erupt it again. It's no doubt much more complicated than that. But we can also get zircon timescales, so measuring uranium, thorium, and these zircons. And that gives us some timescales between these events as well. And while this is not exactly right, 4,000 years or so, these timescales are actually very similar to what we get when we look at this extraction timescale. Okay, so this is giving us a way to link in these dynamic calculations with something we can actually measure in terms of timescales. You might question, well, are these, if you have a much more complicated system than just a body of melt that's never being reintruded, because we know anytime you go out to a Pluton, you see that there are mafic enclaves and things like this. So it's a very complicated open system process. And it's true that you can potentially reabsorb some of these zircons. But if you kind of put this in the calculation, a lot of the stuff in the mush, which is kind of this high crystalline light blue region, seems to retain its zircon record fairly well, even through multiple intrusions. So this is a calculation where we just randomly intruded saltic melt into the system. Okay, so we still kind of retain this zircon repository. Okay, you can do stuff like this for the lower crust as well. I was focusing on the upper crustal system. And what you see with these lower crustal calculations, you do sit around at pretty low melt fraction for long periods of time. Using reasonable basalt fluxes into the crust, you can sit around for hundreds of thousands of years with very small melt fraction, we think, at least using estimates from basalt that we've looked at in the past. Okay, so you get this idea where you can actually spend a relatively short period of time in these repositories. It doesn't take too much time to extract melt from the upper crustal repository, so it gives us kind of a short time scale. But we can also sit around for very long time scales in the lower crust, which is very thermally advantageous. Right, so you can kind of combine these, and then it's just a matter of whether you sat around in this lower crust or you've been sped up and gone through an upper crustal system, or maybe you just bypassed everything and you've gone right from the wedge all the way to the top, very fast time scales. Okay, so that's just kind of indicated here. So what I want to do in the last little bit here is talk about explosive things. So it's a good way to end the day, maybe. And so this is just to remind myself that we're talking about things fragmenting. So what I'm going to do in the next little bit here is talk about multiphase processes where we're dealing primarily with a gas as our fluid phase and glass particles or pumice as our particle phase. And the first thing I want to do is try to put some time constraints on eruption duration for very large eruptions. So I'm going to do this at a system called the Coast Plateau Tuff. Kos is an island off the coast of Turkey. It's a Greek island off the coast of Turkey. So this is reconstructed for past sea levels, but this is part of Turkey here. The island of Kos is there. And so the idea is at the time of this eruption, it produced 100 cubic kilometers, roughly, of high silica rhyolite. If you look at the deposits, so this Kos has made the news a lot lately because it's very easy to get from Turkey to Greece there. So you may have, seen it in the news recently, but it's all one big tuff there. And so this is all the Coast Plateau Tuff. Flows that went over water are missing some of the bigger particles, but still went quite a distance over water, which is fairly remarkable. It's not really a topic of today. But flows that have gone over land have transported really big particles. So I want to use some of the observations from the eruption deposits to constrain basically the duration of this particular eruption. So here we have this coast system again. And what I'm showing at the top here, and I won't get into it in great detail, is different fluxes of material coming out of the conduit. The way these calculations are done, we have a gas phase and we have a particle phase. And the kind of constraint that we place on these is we assume that the flow is choked coming out of the vent. This is a very common assumption in the volcanic literature. The idea here is that this is a compressible fluid dynamics problem. As we add in particles, we're lowering the sound speed of the material, and so we're basically increasing the amount of particles in the flow, but decreasing its velocity. We're pinned down to that speed of sound. Now, in reality, there's probably a good deal of slip between some of the particles in the gas if the particles are large. We're not going to worry about that effect here. What you get with a situation like that is if you have a really concentrated but low velocity mixture, which is the highest flux case over here, it tends to collapse very easily, and the flows that it produces, the gravity currents that it produces, don't go very far. And so you can see from observations from the deposits that these are not really good cases for producing that style of eruption. You can find some sort of middle ground flux where you still produce pyroclastic density currents, and they go about the right distance. But then if you increase the velocity of the mixture even faster, it entrains enough atmosphere and becomes buoyant. So the idea is you're tuning this to basically produce the flows that you see in the deposit. And it turns out the way to corroborate this is to see what the carrying capacity of particles are in the flow as well. So these are field data from big lithics. These are particles that are carried by the flow compared to simulations of Lagrangian dynamics. So if you use this kind of happy middle ground, it produces a lot of the lithics, or the big particles we see in the flow. In other words, it has a carrying capacity that's consistent with this size of eruption. So this is nice. It tells us kind of what flux could produce these sort of deposits. And we can summarize lots of calculations in a regime diagram like this. Here I've plotted the vent velocity times volume fraction, that's alpha in this case. I plotted two different types of simulations, one where we have a ring fracture caldera system, another where we have a central vent, and then vent area is plotted on this x-axis in a log scale. The kind of light shaded region are simulations that collapsed, and the open circles are simulations that produce buoyant plumes. And what I plotted here, because we know the total eruption volume and we know the vent velocity, we've calculated vent velocity, volume fraction, vent area, you can create these timelines, and that's what I've done here. And the kind of this small little area here is what we consider our best fit case in terms of producing flows that have gone the right distance and carried the right amount of lithics. And you see that the sort of timeline for these sort of duration is, around a day or so. You're producing this, big volcanic eruption on the order of a day. That's our estimate. And that's kind of interesting. We never obviously witnessed a really eruption this large, but it kind of makes intuitive sense. This should be about a day or so of eruption. There could be pauses in this eruption. The calculation doesn't really treat that kind of thing. The other two topics I want to touch on relate to instabilities that you can get in these granular multiphase flows. And these don't really directly apply necessarily to more viscous systems, but there can be some analogy. The first instability is a conduit instability that I want to look at. And this is a conduit instability associated with post-fragmentation flow. So the idea is that we've fragmented, we produced these particles, and now I'm going to look at this case where we have gas and these particles. They're going to accelerate from that fragmentation front out to the surface in the atmosphere, and I'm going to look at the dynamics between these particles. And one of the things I'm going to key on is how often these particles break up. These particles are being accelerated from 5, 10 meters per second to the speed of sound of this mixture, so they have a lot of energy in their impacts. And so we can quantify how often particles break up with lab experiments. This is kind of an example of how you might incorporate subgrid information. This just shows impact energy on this axis versus the fraction that break up. These circles indicate the number of experiments that you had break up, and you see that as you get higher energy, you get more and more particles breaking up. That's not too surprising. We can look at a curve like this and also think about the probability that we have a collision at that particular energy and get a joint probability distribution that will then incorporate into our continuum model to look at breakup. And so before throwing the full numerics at it, we can look at a simpler analytical model that's going to make three kind of big assumptions, but interesting assumptions, I think. The first assumption I'll use is that the exit velocity is choked, so speed of sound coming out of the vent. The second is that the parcel timescale, so the timescale from fragmentation to going out the surface, is basically going to be related to the length of the conduit. And the third is that this dissipation of granular energy is related to production due to shear. This is a simple, really simple kinetic theory assumption. So we're going to treat the particles a little bit like a modified gas. We're going to treat the collisions between particles as inelastic, but still exchanging momentum due to collisions. So if you do a simple calculation looking at collision rate, where this theta here is a granular temperature, you compare the fraction disrupted to that, or multiply it by that, and also look at the time scale. What you can get are the fraction of particles that have broken up versus particle diameter. Bigger particles are going to have higher energy, going to tend to break up a little bit easier. And what you see that is if, this is for material properties of pumice and dense glass, but let's just focus on pumice. What you see is that as you get progressively deeper fragmentation fronts, your probability of breaking up these particles becomes much bigger. So the implication here is that if you have a deep fragmentation front, you shouldn't be
preserving many big particles. You should get a mixture that's finer grained, and a finer grained mixture is going to tend to couple with the gas more readily. So it's going to impact the eruption dynamics. You're going to be adding these really fine grained particles that stick with the flow. You can do something similar for calculations. The reason why you might want to do this is that there are feedbacks between the gas and the particle system. And one of the interesting feedbacks you get are these instabilities, especially with the larger particles. You see the sort of clustering behavior. And what's happening here is as the particles start hitting more and more particles, they tend to concentrate and then leave void areas that are relatively low concentration. And so this produces a little bit of pulsing flow. And so maybe one way to produce a little bit of pulse flow right at coming out of the vent. It's a way of basically perturbing the steady state. Okay, the last topic I want to touch upon real briefly is actually has a little bit to do with what Chris was talking about in terms of some things we sometimes gloss over with continuum assumptions. And that's looking at these formation of pyroclastic density currents. And this is looking at a pretty small system. This is Tungurahua in Ecuador. You can't see much going on in below there. But the model that we're going to look at is going to assume that, that we have a dilute system, which is fairly low concentration of particles, overlying a bed load that has high concentration of particles. Now, the dilute system has been explained very well by work that Herbert Huppert has done and coworkers, and in terms of gravity current models. I'm going to focus today mostly on the basal part of the system. And so these are simulations that are very similar. You get, this is showing concentration, so red is high concentration. You get these flows at the bottom that are high concentrated following the gullies. And if I take a look at what these gullies look like, you can see that oftentimes they're very erosional. So these are really high energy flows. So even though these flows look very big, the thickness of this bed load region is a few meters probably. Actually very difficult to resolve with continuum methods. The simple-minded way of thinking about how to get at forces at the bed might just be look at the continuum bed shear stress. That's what's been done here. But we've worried a lot about how maybe the average shear stress or average collisional stresses are not really what's doing the erosion. It might be something in the tail. And that's motivated these very, very, very simplified experiments where we've just taken a granular material, or disk in this case, put it in a hopper and let it flow down this chute and looked at the forces in these particles. These are photoelastic particles. They're like sort of soft plastic. And if we put them between cross-polarized light, they'll emit different amounts of light through the polarization. We can calibrate this light, this optical activity in terms of force. So basically we have all these little stress meters, force meters. And so we can look at these flows. What you see is especially in this fairly small flow, is that it's not behaving like a continuum. You get these big things that look like lightning that are force chains. These lineaments you see terminate often at the bed, and if you were to put a little force meter there, you'd see oscillations of force at the bed at those locations.
Can you show one more time?
Yeah.
Slow it down.
I wish I could. Yeah, with this, I can. Yeah. So if we just pick out one spot on the bed for different types of flows, you get 4 spots like this. The forces here are tiny. These are pretty small particles. if you were to use sort of depth average approach, you would of course predict something in intermediary here. And so this is one of those cases where I think averaging over this and looking at the average force on the bed probably would not be very useful for looking at erosion. Right? The erosion is probably some sort of threshold phenomena that if you exceed a certain threshold, you're going to start to erode. I think this is one of those cases. So I think with that, I probably should wrap up here. Oh, wrong slide. Sorry. I think I didn't mean to do that. Anyway, I think I'm into my exercise here.
We started a little late, so don't.
Oh, okay, okay. I was just seeing that time lining out. Oh, 7:02. There we go. Okay, so I just want to summarize. I think what I hope to show is that this sort of thermodynamic coupling with multi-phase flow can be useful if you're wanting to like comparison between observables, like chemical composition, and start to link that back to dynamics. And I think that's, for our group, is one of the most interesting things. We want to make a link between a lot of the things that are being measured by geochemists, but try to give it a dynamics overview. And then hopefully I showed you how we can also start to link this to timescales using things like zircons. And I talked a little bit about eruption dynamics. I don't have it here in the summer really, but I hope I have also showed you that there are some phenomena, like say the erosion phenomena, that are really sensitive to probably the tail of the distribution. And how we deal with that in terms of creating subgrid rules is going to be a big question moving forward, I think. Like that, I probably should stop here.
Okay.
Questions?
Okay, I have two questions. One is first topic, and then so your analysis should depend on initial composition, isn't it? Because melt fraction temperature relationship depends on.
Yeah, that's right. Yeah,
and,
yeah.
For example, rhyolitic crust or granitic crust, maybe melt fraction change very narrow.
Yeah, that's right. That's right. Yeah.
How about the effect of?
So it's true that when I plot things in terms of melt fraction, it doesn't change much. But if I plot things in terms of amount of silica, it's actually kind of what we were showing with the coat epoxy plot, where you're producing different phase equilibria, and it's narrowing that window, and that's a case where the phase equilibria are governing that. Typically, with the case of low pressure differentiation of say a day site or something, you get pretty decent leverage. If you do the same thing in the lower crust, you don't get much increase in silica. I don't know if that answered your question, but.
And second question, can I? Is the second topic on conduit flow?
Yep.
You are showing choking condition at the top,
That's right.
but maybe there should be another freedom with pressure. How do you determine?
I guess at that case we were just using a pressure balanced jet. Yeah, it could increase. Actually, we don't assume that in the numerical simulations. For the analytical one, we have to basically fix it. That means we're assuming something about pressure. But with the numerical solution, we have a pressure drop. There's a pressure drop from the bottom of the fragmentation front to some point higher in the atmosphere, so it allows the pressure to vary at the exit of the vent. It's a 2D simulation, so we can vary pressure at the vent. And actually, we can get a little bit of slip velocity difference between the particles and the gas in that case, too. So it's not the single-phase choke velocity necessarily. It varies a little bit from that.
Yeah. In the secondary fragmentation modeling
Yeah.
of the collisions, what do you do to the particle sizes when you decide there's been a disruption?
Basically, I bin them, and then I decide, once there are enough collisions, I kind of go to the next bin level, right? So.
Like you had a video there of busting a Prince Rupert's drop.
Yeah.
1 centimeter size drop to a trillion submicron drops.
Yeah, it turns out, so the energies we were looking at in terms of disruptive collisions, you're producing sort of a power law distribution. Turns out if you Clyde pumice at low velocity, it does a little bit like this Prince Rupert drop case where you're producing a lot of fine particles. But in this high energy collision, we're producing particles of all sorts of different sizes, and so we just bin those. Yeah, it's a continuum cheat for sure, but at least we're keeping track of 4 or 5 different grain sizes.
You commented early on by using sort of the MELTS program that you would get surprises.
Yeah.
What was the surprise?
Well-
That you wouldn't have gotten from something like a more simpler back of the envelope type.
I think just in terms of thinking about, say, longevity of magmatic systems, this latent heat variation over such a wide range, I think is not a surprise probably to Paul, but to me, in terms of, and to anybody else doing thermal models, this, this is a big change, right? You're oscillating over, we worry about small changes in thermal conductivity, but these oscillations in latent heat are very large. So in terms of thinking about duration of systems, I'd say that is important.
Any more questions? Okay, well, it's after 5, and what's your,
I think it was an advert.
Oh, yeah.
Do an advert.
about Interpol?
Yeah.
Interpol.
Yeah. Imagine you don't have to know that.
Let's thank our speaker.